Good morning, boys and girls, and welcome back. Today we're continuing our discussion on power series and intervals of convergence and radii of convergence. We're going to talk today about, when we manipulate our power series, we, take the derivative of them or, integrate them. Does that change the interval of convergence? And so that's going to be the focus of our point today. All right, so let's dive in. Should be a quick little fun lesson. All right, here we go. Let's look at this power series here. All right, looks, friendly enough. Let's first, write out the terms of this, a few of the terms, again, just so we can see what it looks like. All right, so if you plug in 1, you would just get x to the first over 1, or x. Plug in 2, I get x squared over 2, x to the third over 3, and so on. Looks similar to the e to the x one, kind of, except for it doesn't have the factorials. Okay, now let's go ahead and let's look for the interval of convergence. So let's start by doing the ratio test. And remember, to do the ratio test, you take the next term and divide it by the term that came before it. So x to the n plus 1 over n plus 1 divided by x to the n over n. But when I divide, I'm going to flip that guy and multiply. So I end up with this step right here. And now I'm going to simplify this. Or I guess at least rewrite it first. Put the n's on the left-hand side and the x's on the right-hand side. And now I'm going to simplify this. If we look as n goes to infinity, again, the plus 1 basically goes away. So this is n over n, and that cancels off. Becomes 1, so I don't have to worry about that part there. Over here with the x's, I'm going to subtract exponents, and when I subtract my exponents, I'm going to end up with just x. So we end up just with the limit as n goes to infinity of the absolute value of x. And so again, we're going to want to check when this is less than 1. So basically, we're just going to look when the absolute value of x is less than 1. All right, let's set up our cases. Okay, and that's going to give us x is less than 1 and x is greater than negative 1. And then, so our interval now we have found is negative 1, which is less than x, which is less than 1. But now we need to make sure we test our endpoints. All right, so again, if we test at negative 1 and plug negative 1 back into the original power series, we get negative 1 to the n over n, which is the alternating harmonic, so that is going to converge. So we would again put a little or equal to up here underneath the inequality for negative 1. And now let's test that x equals 1. And when I get 1 to the n, that's just 1 over n. And so this would be the harmonic. So this side is going to diverge. Again, show people you're testing endpoints on an FRQ. Make sure you say why you know things converge or diverge. State the test that you are using. But in this case, our interval of convergence is from negative 1 to 1, including negative 1, but not including 1. All right, that was a nice little review of Part 1, Power Series Part 1 stuff. But now let's take this and let's go play around with what if we integrate f of x. Again, f of x is a series we just played around with. Let's go integrate this and see what happens. All right, well, let's start by rewriting f of x again. f of x was x to the n over n, right? That series, or x plus x squared over 2 plus x cubed over 3 plus x to the fourth over 4. So if we integrate this polynomial, plus I should say dot, 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 if we integrate this polynomial, we're going to end up with something like x squared over 2. Because again, to integrate, we're going to add 1 to the exponent, right? And then divide by the new exponent. Plus x cubed over, and then I rewrote this as, if I add 1 to x squared here, I get 3, and then I got to divide by 3. So I wrote that just as 2 times 3 here. Okay? And then plus x, same thing with the rest here. X to the fourth over 3 times 4. Plus x to the fifth over 4 times 5. So I've integrated this, and then every time I divide, I didn't put the numbers together. I just have to multiply it out. And the reason why I'm writing it like that is because now what I'm going to want to do is I want to write the nth term, or I want to write I want to write this series using series notation. And writing this nth term gets to be a little tricky. Again, we generally want to start with n equals 1 as our first term going to infinity. And now I want to, try to find out our pattern here. So on the top, we still have an x to something, right? X to the n, really, and if I look, it's x to the n plus 1, right? So if I plug in 1, I get 2. If I plug in 2, I get 3. If I plug in 3, I get 4. All right, so that's kind of making some sense. Now, over, maybe I should have, looking at here, I didn't do the first one like this, but maybe I should have left the first one like this too, so we can kind of see what's going on. And that's why I kind of have these other numbers here. Over Well, it looks like the first number here is our n, right? Our first term, second term, third term, fourth term. And then I'm multiplying it times n plus 1. That's why I didn't want to multiply those together. I wanted us to see that connection there. All right. And if we think about it, this is basically if I would just integrate this term up here, right? I'm going to add 1 to the exponent. So this becomes x to the n plus 1. And then there was an n on the bottom, but then I got to divide by that new exponent. Right? So you can actually like take the derivative or integrate, you know, the series themselves as well to come up with that nth term. That's what I want to point out a little bit. All right, but now we got our new series here that we've integrated. Now let's find the interval of convergence for it. So setting up our ratio test, we get something that kind of looks like this right here, right? The next term divided by the current term or previous term. And when I organize it, it's going to look something more like this. N times n plus 1 over n plus 1 times n plus 2. And x to the n plus 2 over x to the n plus 1. And now when you simplify, the n plus 1s would die off. And so we're going to be left with something like, well, those would disappear. I guess we can just still evaluate the limit from right here. So I'd have n over n plus 2, which I would do the limit as n goes to infinity. That's going to be n over n or 1, so that disappears. And so again, if I subtract exponents here, n plus 2 minus n plus 1. See my work to the side here. Again, that's just going to equal x to the first. So again, when I work this all out, I'm still just going to be dealing with the absolute value of x, and I want to know when, again, that's going to be less than 1. So just like last time, setting up our two cases, extra work down here, setting up our two cases, we are going to get, you know, just our negative 1 is less than x less than 1, just like we did the first time. Okay, so this has the same interval as the original function we have found. All right, now let's test our endpoints. Okay, so we're going to plug negative 1 back into our original series, x to the n plus 1 over n times n plus 1. And in this case, we get an alternating series again, right? And that is going to pass the nth term test as n goes to infinity. That will go to 0. And they will get smaller as n gets bigger. So this is going to converge by the alternating series test. And again, because it converges by the alternating series test, I need to put a little or equal to on the negative 1. All right, now let's test the other endpoint. Oh boy, I wonder what's going to happen here. Is it going to be the same as the original one? What do you all think? All right, so this is going to give us 1 to the n plus 1 over n times n plus 1. And 1 to the n plus 1 is still just going to be 1 over n times n plus 1. Or this would be like 1 over n squared plus n, which if you compare that, use direct comparison to compare it to a p-series, 1 over n squared. 1 over n squared plus n is always going to be smaller than 1 over n squared, since it's got that extra bit that makes it bigger on the bottom. And so since it's always smaller than 1 over n squared, then by direct comparison with p-series, it is going to have to converge. So what do you know? This converges differently than, again, the other one just converged on negative 1. Now this is converging on both sides, okay? So the interval stayed the same, but I had different endpoints. All right, let's play around one more time, and let's look at the derivative of our original series. All right, so again, just for reference, we're going to take the derivative of our original function. I wrote out, what our function was here so we can just, look at it and kind of see. Let's first maybe try to play with our series this time. And we said, hey, instead of taking the derivative, which we totally could of this, let's try taking the derivative of this first, okay? Let's actually try to take the derivative of our series. If I had x to the n over n, and I was going to take the derivative of that, again, I multiply the front by the exponent, so I multiply this 1 over n by n, so the bottom disappears, and I'd be left with x to the n minus 1, okay? And that would be my new series. Let's see if that's going to work. All right, this is what we're saying it's going to be. So if we look at the derivative of f of x, we get 1 plus x plus x squared plus, that'd be x cubed. And look, that is the nth term for that function right there. That would represent it. So again, you can do it either from the function and write your nth term, or you can just play around with the nth term of your, series and, integrate or take the derivative of those things. Anyway, now let's look at the ratio test of this again to find our interval of convergence. If we add 1 to x to the n minus 1, we just get x to the n. So this would be set up as x to the n over x to the n minus 1. And again, as I do my limit as n goes to infinity, well, a couple things. There's no n part, just the x part this time, right? So I could take this and I could subtract exponents first. And again, we're just going to end up with limit as n goes to infinity of x. And we want to find out when this is going to be less than 1. All right? And we already did that. We set up the two cases, right? And we know already. So again, our interval did not change, right? The interval is staying the same, but let's test endpoints one more time on these. So first we're going to plug -1 again into our series. And now this is going to diverge because it fails the nth term test for convergence. As I look at the limit as n goes to infinity, that's not going to go to 0. The series here would look something like 1 minus 1 plus 1 minus 1. So this fails the nth term test. All right, let's go ahead and test our other endpoint now. Let's test that x equals 1. And you can see that the same thing happens. I get 1 to the n minus 1 now, so this series goes 1 plus 1 plus 1 plus 1 plus 1 plus 1. A little bigger there. But this one, again, it's going to fail the nth term test as well, so this also diverges. So in all three cases here, we see that, the interval does not change when you manipulate a power series. The interval is always going to stay the same. That's kind of handy to know. But what does change is the endpoints, okay? So that is the moral of today's story, boys and girls. Operations do not change interval, just the inclusion of endpoints. Play around with power series some more today. If you got questions, come find me. Otherwise, it was great being with you again, and I'll talk to you again real soon.